I want you to just take a nice deep breath.
Just let the tension of the day kind of fall away.
Exactly. Look at your hand for a second. Look at the room around you.
Or if you're outside, look at the trees or the sky.
Yeah, everything you can see, touch, smell, interact with every star, every planet, even the cells in your own body. It all makes up just 5% of reality.
Just a tiny sliver.
Right. The other 95% is this hidden ocean, an ocean of invisible forces, missing twins, and mathematical ghosts.
It's a very quiet, very mysterious universe out there.
It really is. Welcome to the deep dive. And before we step off the edge of the map into that hidden ocean, I want to gently invite you to like and subscribe to Decoding the Dark.
Your support is, well, it's what allows us to take these journeys.
Exactly. It helps us keep charting these relaxing, awe-inspiring journeys into the unknown cosmos. So today, our mission is to explore that invisible 95%.
We're going to unpack a really fascinating stack of sources together.
Yeah, sources that challenge the fundamental nature of existence. We're going to search for the missing mirror image of our reality.
We'll trace the invisible web holding our galaxy together, too.
And we'll feel the unseen force that is actively pushing the universe apart. We're even going to wrestle with this completely bizarre concept of negative mass.
Before finally looking out to the absolute horizon of time just to see how this cosmic story ends.
Right. And I'm joined by our resident expert today. Our goal here isn't to drown you in equations or math.
No, not at all. There is no math test at the end of this.
We just want to take these massive, mind-bending realities and connect them right back to the quiet atoms sitting right there in your living room.
It really is a pleasure to be here. And, connecting it to the listener's living room is exactly the right place to start.
It grounds it, I think.
It does. Because when we talk about the dark universe, it's so easy to feel detached. Like we are discussing something happening billions of light years away.
Like it's just sci-fi or something.
Right. But this unseen 95%, it's the environment we actually live in, is passing through us right now, quietly.
That's a beautiful way to think about it.
So we are going to explore these concepts gently. We'll trace the mechanisms of how they work, step by careful step.
There's absolutely no rush today, just the pleasure of understanding the strange machinery of the cosmos.
Exactly.
So to begin, I want to look at the 5% we actually understand, the regular matter, and I want to look at its reflection. We are starting with antimatter.
A wonderful place to begin.
The sources use this brilliantly grounded analogy for this, and I want you to picture it. Imagine you are standing in a perfectly flat, quiet field of dirt.
Just a calm, open space.
Right. And you take a shovel and you dig a single hole. In that one action, you've created two distinct things.
The dirt and the space it left behind.
Yeah. You have a pile of dirt resting on the ground, and you have the exact corresponding hole in the earth. You literally cannot create the pile without creating the hole.
They're born in a perfect pair. Exactly.
And in quantum physics, that pile of dirt is matter. The stuff making up the shovel, the field, and you. And the hole is antimatter.
That analogy perfectly captures the symmetry of it all. Because antimatter isn't the theoretical fiction. It is a physical reality governed by absolute, unbreakable symmetry.
Like looking in a mirror.
Yes. If you look in a mirror, the reflection mimics your movements exactly, but left becomes right. Antimatter is that reversed reflection, just at a subatomic level.
Okay, so let's look at a single atom.
Sure. The core of a normal atom contains protons, which carry a positive electrical charge.
Right, the positive building blocks.
The mirror twin of the proton is the antiproton. If you were to place an antiproton on an impossibly precise scale, it would weigh exactly the same as a normal proton.
So the mass is identical.
Identical. It has the same mass, the same spin, but its electrical charge is negative. It is the exact quiet opposite.
And orbiting that core, we have the electron, which is natural negative.
Exactly. And its twin is the positron, which has a positive charge. Nature demands this balance.
So for every piece of the puzzle that builds our reality, there is a counterpart piece that looks identical but carries the opposite charge.
It's a beautifully balanced system.
But what really blows my mind is that this isn't just something happening in a massive underground particle collider somewhere. It's happening in hospitals.
It is. Every single day.
The sources point out that PET scans positron emission tomography literally use antimatter to look inside the human body.
They do.
But how does that actually work? I mean, how are doctors putting antimatter into a patient without causing a total catastrophe?
Well, it's a remarkable piece of medical engineering. And it relies entirely on the fundamental rule of how antimatter behaves.
Okay, walk me through it slowly.
In a PET scan, a patient is injected with a safe, biologically active molecule, like glucose. And that glucose has been tagged with a radioactive isotope.
So it's like slightly glowing sugar.
Essentially, yes. As this isotope undergoes natural radioactive decay inside the warm, quiet environment of the body, it emits a positron.
An antimatter electron. Okay, so there is actual antimatter floating around in the patient's bloodstream.
Yes, but only for a microscopic fraction of a second. That positron travels perhaps a millimeter through the surrounding tissue.
Just a tiny distance.
Right, and then it encounters a regular electron. And this brings us to the ultimate rule of the mirror reality. Matter and antimatter cannot touch.
They just absolutely cannot coexist in the same space.
No. The moment that positron and electron collide, they annihilate each other. They vanish completely.
Just erased from reality.
Exactly. Their mass is converted 100% into pure energy. According to Einstein's famous equation, E equals mc squared.
So they turn into light.
Yes. In this case, the annihilation produces two high-energy gamma rays that shoot out of the patient's body in exactly opposite directions.
Wow, and the scanner catches them.
Right. The scanner is a giant ring of detectors. When it detects two gamma rays hitting opposite sides of the ring at the exact same nanosecond, the computer draws a line between them.
That is so elegant.
It is. Millions of these annihilations happen. Millions of invisible lines are drawn, and where they intersect, the doctor gets a perfect, high-resolution 3D map.
A map of where the glucose is being consumed.
Yes, which often reveals the location of a tumor. So we are gently harnessing subatomic annihilation to save lives.
That is just staggering. We use the destruction of the universe's missing twin to heal a human body.
That's a wonderful irony.
And the sources point out an even more domestic example, which I love. A simple banana sitting on your kitchen counter.
Ah, yes. The radioactive banana.
It emits a positron roughly every 75 minutes, like just sitting there next to your coffee maker.
Bananas are rich in potassium, and a tiny fraction of that is a naturally radioactive isotope called potassium-40.
So as it decays,
it occasionally releases a positron. So your fruit bowl is quietly breathing tiny, fleeting whispers of antimatter into your kitchen.
I just find that so incredibly soothing to think about. The universe is just humming with these invisible processes all around us.
It never really stops.
But let's scale up that annihilation rule for a second, because you touched on E equals mc squared, and I think we really need to dwell on the sheer efficiency of that conversion.
It is quite profound.
When you say 100% of the mass is converted to energy, that is, that's unlike anything we experience in our everyday normal lives.
It is entirely alien to our normal experience of the world. Think about burning a log in a peaceful campfire.
Sure, you get the crackle, the heat.
It feels very energetic. You get heat and light. But chemically, it is incredibly inefficient.
How so?
The fire just breaks the chemical bonds between the atoms in the wood. It releases a tiny bit of energy, but the atoms themselves remain.
Right, you're left with ash and smoke.
Exactly. You are left with charcoal. You have converted an infinitesimally small fraction of the wood's actual mass into energy.
Basically just rearranging the furniture.
Precisely. Even if we look at the most devastating forces humanity has unleashed, like nuclear fission or fusion weapons, we are only converting roughly 1% of the material's mass into energy.
Only 1%.
Yes. The rest is just blasted outward as physical radioactive debris.
But with antimatter, there is no ash.
None at all. There is no debris, there are no leftover pieces.
It's just a clean slate.
When a proton and an antiproton touch, their physical mass ceases to exist. It is a perfect, quiet erasure. All of that mass becomes pure, radiating energy.
That is just so hard to visualize.
If you had just 1 gram of antimatter and you let it gently touch 1 gram of normal matter, the resulting explosion would be roughly equivalent to the atomic bomb dropped on Hiroshima.
Just 2 grams total.
Yes, 2 paper clips worth of material completely erased, releasing city-leveling energy.
Which brings us to the ultimate cosmic paradox. The deep mystery of why you and I are even sitting here to have this conversation at all.
A great survival story.
Exactly, because if we rewind the clock back 13.8 billion years to the Big Bang, the universe was just pure, unimaginably dense energy.
A very chaotic, very hot place.
Yeah. And as it cooled, that energy condensed into physical particles. And the laws of physics state that this process absolutely must create matter and antimatter in equal amounts.
50-50. For every pile of dirt, a hole must be dug.
Right. But the early universe was also incredibly dense. all those particles were crammed together.
There was no room to hide.
So if you have equal amounts of matter and antimatter crammed into a microscopic space, they can't avoid each other. It should have been an immediate, total slaughter.
Matter and antimatter colliding, annihilating into light.
And turning back into particles and annihilating again? The two sides should have waged this war of total erasure until absolutely nothing was left,
The dirt should have fallen perfectly back into the hole.
leaving a flat, empty field. The universe today should just be nothing but a vast, silent ocean of cooling radiation.
No galaxies, no planets, no carbon, no us.
No us. By all elegant mathematical logic, the universe should be completely empty.
It is a sobering thought.
So, my first instinct when reading this, and I'm sure this is what early astronomers thought too, is, well, why couldn't the antimatter just be hiding?
It's a very natural question to ask.
Right. Why couldn't it have been separated in the chaos of the Big Bang? Maybe there is a sector of the universe, billions of light years away, just filled with antimatter galaxies.
Antimatter stars, antimatter planets, just peacefully existing.
Yeah, completely separated from us by a vast ocean of empty space.
It's the most intuitive solution. We desperately want the universe to balance its books. If the antimatter isn't here, it must be over there.
It just makes sense.
But modern astrophysics has ruled this out with a very high degree of certainty. We have looked for it carefully.
How do you even look for that?
We use instruments like the Fermi Gamma Ray Space Telescope to scan the deep, quiet cosmos. You see, space is not a perfect vacuum.
Right, there's always a little bit of stuff drifting around.
Exactly. Even the vast, dark voids between galaxy clusters are filled with incredibly thin, diffuse clouds of intergalactic gas.
Just stray hydrogen atoms drifting in the dark.
Yes. Now imagine a region of normal matter galaxies borders a region of antimatter galaxies.
Okay, I'm picturing it.
The galaxies themselves might be millions of light years apart, but those thin clouds of gas surrounding them would eventually drift together.
Like clouds touching in the sky.
Exactly. At the border where the matter gas meets the antimatter gas, particles would inevitably touch.
And they would annihilate.
Yes. You would have continuous, relentless annihilation. This border wouldn't just be an invisible line, it would be a blazing wall of gamma radiation.
Wow. Just a massive cosmic fence of light.
It would light up the cosmos with the specific energy signature of proton-antiproton annihilation.
Yeah.
We would see these radiant, glowing scars across the night sky.
Marking the territories of the mirror universe.
Right. But we don't see them.
We don't see anything like that at all.
We don't. We have mapped the sky. We have looked back toward the dawn of time. The sky is dark and quiet.
There are no glowing walls.
There are no glowing walls of annihilation. The antimatter isn't hiding behind some cosmic curtain. It is truly fundamentally gone.
Which means we are the leftovers.
We are.
We are the survivors of a cosmic massacre. Let that just sit in your mind for a second.
We call it the baryon asymmetry problem. It is perhaps the greatest unsolved mystery in particle physics today.
Because in the first fractions of a second of existence, that great war of annihilation actually did happen, didn't it?
It did. 99.999999% of all the matter created in the Big Bang was destroyed by its antimatter twin.
Just gone.
The universe effectively hit the delete button on itself.
That is terrifying and beautiful at the same time.
The energy from that massive annihilation is still visible today, actually. It's the cosmic microwave background radiation.
The static hiss left over from the dawn of time.
Exactly. The ash of the cosmic war.
A beautiful way to put it. But nature made a mistake. It missed a spot.
For some unknown reason, there was a microscopic imbalance. Just a tiny flaw in the symmetry.
For every 1 billion particles of antimatter, there were 1,000,000,001 particles of matter.
A tiny, seemingly insignificant rounding error.
When the Great Annihilation concluded, the billion pairs calmly canceled each other out. But that one extra particle of matter had no partner to destroy it.
It survived the fire.
It survived. You are looking at a universe built entirely out of that 1 in a billion leftover rounding error. Everything you see, every star in the sky, the phone in your pocket.
The very air you breathe.
It's all made of the survivors. It reframes existence in a way that is just really hard to shake.
It gives a profound weight to our presence here.
It does. You aren't just made of stardust, you are made of the stubborn ashes that refuse to burn.
It certainly makes you want to understand how matter managed to cheat the system.
Absolutely. Like, did a fundamental law of physics break down for a millisecond to create that extra matter particle?
To figure that out, we have to capture the ghost. We have to study antimatter today, right now.
But how do you study something you literally cannot touch? Any container you build is made of matter. Glass, steel, plastic.
If you put antimatter inside it, it touches the wall and explodes.
Right. So this takes us to CERN, the massive particle physics laboratory in Europe. But we aren't talking about the Large Hadron Collider, the machine everyone knows.
No, the Large Hadron Collider, the LHC, is essentially a sledgehammer.
It's about smashing things.
It is designed to accelerate protons to near the speed of light and smash them together with apocalyptic violence.
Just to see what fundamental particles fly out of the wreckage.
Yes, it is a machine of pure, hot kinetic energy. But to study antimatter, to ask it delicate questions about its nature, you cannot use a sledgehammer.
You need a softer touch.
You need absolute patience and absolute cold. At CERN, they have a facility dedicated to this, featuring machines with names like the Antiproton Decelerator, or AD.
And the Elena ring.
Yes.
The decelerator.
Yeah.
Doing the exact opposite of the LHC, slowing things down.
Precisely. When scientists create antiprotons, usually by firing a beam of high-energy protons into a block of metal, the resulting antiprotons are born wild.
They're angry.
They emerge traveling at a significant fraction of the speed of light. They are hot, chaotic, and impossible to study.
Because if you tried to look at one, it would cross your laboratory and annihilate against the far wall before your detectors even registered it was there.
Exactly. You cannot examine a bullet while it is in flight.
You have to catch the bullet very, very softly.
Yes. So the AD catches these wild antiprotons and forces them into a magnetic track. It applies complex electromagnetic brakes, gently slowing them down.
And then they are passed into the Elena ring, right, which acts as this profound cosmic freezer.
It does. Elena utilizes a brilliant technique called electron cooling.
Okay, please explain how that works, because cooling a subatomic particle sounds incredibly difficult. You can't just, put it on ice.
No, you use the physics of temperature itself. Temperature at a subatomic level is simply speed.
Fast particles are hot, slow particles are cold?
Precisely. In the Elena ring, they inject a parallel stream of perfectly cold, highly organized normal electrons.
So they have two streams running side by side.
They run this cold stream alongside the chaotic hot antiprotons. As they travel together, the hot antiprotons physically bump into the cold electrons.
Just little microscopic nudges.
Yes. With every microscopic collision, the antiproton transfers a tiny bit of its kinetic energy, its heat, to the electron.
Oh, wow. It's exactly the same thermodynamic principle as pouring cold milk into a hot cup of coffee.
That is a perfect analogy. The fast molecules bump into the slow ones until they reach a calm equilibrium.
So the milk cools the coffee.
By the time the antiprotons exit Elena, they have been stripped of their violent energy. They are moving at walking speed. They are calm.
And once they are calm, you can finally trap them. But again, you can't use a physical box.
You have to use invisible walls.
This is the penning trap. I read the breakdown of this in our sources, and it just sounds like a magic trick.
It is a marvel of human ingenuity.
You have a vacuum chamber, completely devoid of any normal air molecules, and you turn on a massive magnetic field that points straight up and down.
A cylinder of magnetic force.
Right. If the antiproton tries to move horizontally, the magnetic field grabs its electrical charge and forces it to spiral in a tight little circle.
Like a marble rolling around the rim of a very steep bowl.
Yeah. It's locked in horizontal space, but it could still escape by drifting straight up or straight down out of the magnetic tube.
Gravity or thermal drift would eventually pull it away.
So they add an electric field, they place metal electrodes at the top and bottom of the chamber and give them a strong negative charge.
And because the antiproton also carries a negative charge, it is repelled by those electrodes.
Exactly, like two negative magnets pushing away from each other.
So when the antiproton drifts up, the top electrode pushes it gently down.
And when it drifts down, the bottom electrode pushes it gently up. The result is pure, stable levitation.
The antimatter is suspended in the absolute center of the quiet vacuum, touching nothing at all, held only by invisible force fields.
Scientists have kept a single antiproton levitating like this for months, just sitting there in the dark.
It is an incredible achievement. But an antiproton is just a nucleus. It's just the core of an atom.
Right, it's not the whole thing.
To really see if antimatter behaves like normal matter, you need to build an entire anti-atom. You need to create antihydrogen.
Which brings us to the LFEHA experiment at CERN. They basically act as subatomic matchmakers.
That's exactly what they do.
They take a cloud of these cold, levitating antiprotons, and they carefully merge them with a cloud of cold positrons, the antimatter electrons.
And when the gentle conditions are perfect, A positron will fall into a stable, quiet orbit around an antiproton.
You have just forged an atom of antihydrogen. You have synthesized the mirror universe in a lab.
But the moment you do that, you trigger a massive, terrifying physics problem.
Yes, and this is where I got genuinely stuck while reviewing the materials because it's so tricky. The Penning trap only works because the particles have an electrical charge.
The magnets and the electric fields absolutely need that negative or positive charge to grab onto.
But a hydrogen atom, even an antihydrogen atom, is electrically neutral. The negative charge of the antiproton and the positive charge of the positron perfectly cancel each other out.
The net charge drops to zero.
Right, so the net charge is zero. So the moment the anti-atom forms, the invisible hands just lose their grip.
It is exactly like a ghost suddenly slipping its chains.
The electric and magnetic fields of the Penning trap become utterly useless.
The antihydrogen atom is neutral. It ignores them completely. It is suddenly free to drift in any direction it chooses.
And the second it drifts a few centimeters and touches the physical metal wall of the vacuum chamber,
Annihilation. The anti-atom is gone in a flash of gamma rays.
just heartbreaking. For a long time, scientists could create antihydrogen, but they could only hold it for a few thousandths of a second.
It was incredibly frustrating for the teams involved.
So how do they solve it? How do you hold something that is completely neutral and untouchable?
The LPHA team had to invent a completely new type of invisible cage. They called it a magnetic minimum trap.
Okay, how does a magnetic minimum trap work?
Well, while the anti-atom as a whole is electrically neutral, the positron and the antiproton inside it are still spinning.
They have a tiny rotation.
Yes, and this tiny quantum spin creates an unimaginably weak, infinitesimal magnetic dipole. It is essentially a microscopic, incredibly weak bar magnet.
So the atom itself has a tiny north and south pole.
Precisely. The magnetic minimum trap relies on this incredibly faint property.
So it's a much more delicate grip.
Very delicate. The team built an intricate, complex arrangement of superconducting magnets that creates a specialized field.
And this field is shaped differently.
Yes. The magnetic strength is weakest in the absolute center of the chamber and gets stronger in every direction as you move toward the walls.
Ah, I see. And because of its tiny magnetic orientation, the antihydrogen is naturally repelled by the strong magnetic fields at the edges.
It is forced to sit peacefully in the quiet valley at the center of the trap.
It is an incredibly delicate operation. It's like trying to hold a bowling ball perfectly still using a single thread of spider silk.
That's a beautiful way to visualize the extreme fragility of the setup. But it worked.
They managed to trap neutral antihydrogen, holding it entirely stable for nearly 20 minutes.
20 minutes of perfect, quiet observation.
20 minutes. They held the deleted universe still for 20 minutes. And once you can hold it, you can start doing some truly wild engineering with it.
Which brings us to the PUMA project.
Yes, PUMA. This sounds less like a physics experiment and more like a high-tech heist movie.
PUM stands for Antiproton Unstable Matter Annihilation. It is one of the most ambitious and logistically terrifying proposals in modern physics.
Because they want to put antimatter in a truck. Let's just state that clearly for everyone listening. They are putting antimatter in a truck.
It sounds absurd, but it is true.
The plan is to build a portable magnetic trap, essentially a high-tech vacuum thermos. They want to load 1 billion antiprotons into this thermos at the decelerator facility.
A billion antiprotons.
Then they want to unplug this thermos from the wall, run it on a generator, load it onto the back of a truck, and physically drive it across the CERN campus to a completely different facility.
We are talking about taking the most volatile substance in the universe out of the controlled, pristine laboratory environment.
They have to worry about speed bumps. They have to worry about the vibrations of the truck engine. They have to worry about a battery failure.
If the power to the magnetic trap cuts out for a single microsecond,
The invisible walls collapse, 1 billion antiprotons hit the side of the thermos, and the entire experiment is vaporized.
exactly.
Why take that insane risk? I mean, what is worth driving that bomb across a campus?
Because of where they are driving it to. They're driving it to a specialized facility called ISOLD.
And what does ISOLD do?
ISOLD is capable of producing incredibly exotic, highly radioactive atomic nuclei. These are atoms that have been artificially stuffed with far too many neutrons.
So they are unstable monsters.
Very unstable. And because they have so many extra neutrons, they develop something called a neutron skin.
A skin of neutrons.
Yes. The protons cluster tightly in the center, and a thick layer of purely neutral neutrons forms on the outer edge of the nucleus.
Okay, so you have this radioactive atom with a thick shell of neutrons. How does driving antimatter across campus help study that?
Because the antiproton is the ultimate delicate probe. It acts like a highly intelligent subatomic missile.
It seeks out the core.
When you introduce an antiproton to this exotic atom, it gets gently pulled in by the positive charge of the protons hiding in the core. It begins to spiral inward.
But before it can reach the core,
It hits the surface. It hits that thick neutron skin. The moment the antiproton touches a neutron on the surface, they annihilate.
But wait, let me pause you there. An antiproton and a regular neutron aren't exact opposites, are they? A neutron doesn't have a positive charge.
That is a very astute observation.
Do they still annihilate perfectly?
They do, because at a deeper, quieter level, they are made of complementary quarks.
Ah, okay. The building blocks match up.
Yes. When they annihilate, they don't just vanish into pure light like an electron and positron. They burst into a specific spray of subatomic shrapnel, primarily particles called pions.
And some of these pions have an electrical charge, and some are neutral.
Exactly. And here's the profound genius of the PUMA experiment. The ratio of charged pions to neutral pions that fly out of the explosion tells the physicists exactly what the antiproton hit.
It tells them if it annihilated with a proton or a neutron?
Yes, by measuring the shrapnel, they can definitively map the thickness and density of that invisible neutron skin.
We use the destruction of antimatter to measure the architecture of radioactive matter?
We use the ghost to measure the monster.
It's brilliant. It's just so brilliant. And speaking of ghosts, there is one more fundamental question scientists needed to ask the antimatter trapped in the ALPHA experiment.
A very simple but incredibly important question.
A question that sounds like it was asked by a curious 5-year-old but took decades of Nobel-level engineering to answer. Does antimatter fall down?
Does it respond to gravity the same way we do, or does it possess anti-gravity?
Does it fall up?
The ALPHA-G experiment, where G gently stands for gravity, was designed to test exactly this. And the theoretical stakes were monumental.
Monumental, because if antimatter fell up, it would mean our fundamental understanding of physics was broken.
Completely broken.
Right. If it falls up, Einstein's general theory of relativity has a massive gaping hole in it. Relativity relies on the weak equivalence principle,
Which states that gravity is simply the curvature of space-time.
It shouldn't matter what an object is made of. A rock, a feather in a vacuum, a planet, or an atom of antimatter.
They all exist in the same curved space, so they should all slide down that curve the exact same way.
If antimatter fell up, it means space-time curves differently depending on the particle's identity. It would just be total chaos.
You could theoretically build a perpetual motion machine. It would upend a century of established quiet physics.
So, and to test this, the ALPHA team built a specialized vertical vacuum tube, a towering invisible silo.
They placed the trapped, neutral antihydrogen atoms exactly in the center of this silo.
And they carefully balanced the magnetic fields holding the atoms, ensuring there was absolutely no upward or downward magnetic pressure.
The atoms were perfectly, quietly suspended in the void.
And then they simply turned the trap off, they opened the invisible doors, and just watched to see which way the atoms drifted.
It sounds so simple, but I imagine the tension in that control room was unbearable.
Gravity is such an incredibly weak force compared to electromagnetism. The slightest static charge, a stray magnetic field from a laptop cord across the room, could push the atom up and ruin the measurement.
The isolation required was unprecedented.
They ran the experiment multiple times, carefully recording where the atoms hit the walls of the tube and annihilated. The lower half of the tube or the upper half.
And the results finally came in, and they were beautifully conclusive. Antimatter falls down.
It accelerates downward at roughly 9.8 meters per second squared, exactly like a rock dropped from your hand, exactly like the rain.
Gravity, it seems, is the great unifier. It treats the mirror universe and our universe with the exact same quiet indifference.
The mirror universe falls just like we do, which provides this perfect, really organic pivot for our journey today.
Yes, from the very small to the very large.
Because antimatter is the visible matter that went missing, leaving us seemingly alone. But the universe presents us with an exact opposite problem on a much grander scale.
An immense, undeniably powerful gravitational presence that is holding our reality together, but that we cannot see at all.
We are shifting from the microscopic quantum traps of CERN to the macroscopic, sprawling scales of galaxies. We are entering the realm of the invisible scaffolding, dark matter.
It is a profound shift in scale.
Yeah.
We're moving from a phantom that was largely deleted from the universe to a phantom that utterly dominates it.
And before we explore its architecture, we really must explicitly clarify what it is not, because the naming conventions in cosmology can be frustratingly confusing.
They certainly can. Dark matter is absolutely not antimatter.
Let's hammer that point home for everyone listening. If dark matter was antimatter, it would be touching regular matter constantly.
Exactly. If the halos of dark matter surrounding our galaxy were made of antimatter, the interstellar dust and gas drifting through space would constantly be colliding with it.
The entire night sky would be a blinding, lethal inferno of gamma-ray annihilation.
We simply would not exist. Dark matter is called dark simply because it does not interact with the electromagnetic spectrum at all.
It doesn't glow.
It does not emit light. It does not reflect light. It does not absorb light. It is completely, perfectly invisible to our eyes, to our radio telescopes, and to our X-ray satellites.
It only interacts with the universe through the quiet source of gravity.
That is its only footprint.
So if it's entirely invisible, how did we ever figure out it was there? It's a classic ghost story. We only know the ghost is in the room because we can see it moving the furniture.
That is the perfect way to describe it.
And the astronomer who first saw the furniture moving in a way that couldn't be ignored was Vera Rubin in the 1970s, building on the earlier, often dismissed work of Fritz Zwicky in the 1930s.
Yes. Zwicky was looking at the Coma Cluster, a massive group of galaxies, and noticed they were moving far too fast.
Like bees swarming too quickly.
Right. If you added up all the visible starlight to estimate their mass, there wasn't nearly enough gravity to keep the cluster from flying apart.
He called it Dunkelmaterie, dark matter.
But his measurements were imprecise, and he was a notoriously abrasive character, so the astronomical community largely ignored his quiet warnings.
It took Vera Rubin's meticulous, undeniable observations of individual spiral galaxies like our neighbor Andromeda to really force the scientific world to confront the ghost.
She was a brilliant observer.
I love the physics of what she discovered because it is so intuitive to anyone who's ever been on a playground. We all understand how a merry-go-round works.
It's a very visceral feeling.
Right. If you stand near the center pole, you can hold on easily. The rotational force isn't that strong. But if you stand on the very outside edge, you are traveling much faster to complete the circle in the same amount of time.
You have to hold on for dear life.
Or the centrifugal force will just throw you off into the dirt. A spiral galaxy is essentially a giant galactic merry-go-round.
The visible mass, the stars, the glowing gas, is highly concentrated in the bright center and gets thinner and thinner as you move to the outer edges.
So based on Newton's laws of gravity, the stars at the very edge should be moving much slower than the stars near the center because there is less gravity holding them in.
That was the absolute logical expectation.
But Rubin meticulously measured the Doppler shift of the light from stars at varying distances from the galactic center. She plotted their speeds on a graph, expecting to see a gentle curve that peaked near the center and slipped downward at the edges.
A declining rotation curve.
But that is not what she found. The curve went up, and then it stayed perfectly flat. The stars at the outermost edges of the galaxy were whipping around the center at exactly the same impossible speeds as the stars near the core.
They were holding on to the merry-go-round, but there was no visible pole to hold on to.
Precisely. Based solely on the visible mass of the stars and gas, those outer stars should have been flung out into deep space millions of years ago.
The galaxy should have torn itself apart like a fragile pinwheel in a hurricane.
The only mathematical solution, the only way to keep the galaxy intact, was to conclude that the visible galaxy we see is just a tiny glowing hub embedded in the center of a massive invisible sphere of mass.
A dark matter halo.
This invisible halo provides the immense gravitational glue required to hold the spinning stars peacefully in place.
And as we look deeper into the cosmos, we realize this invisible glue wasn't just wrapping around individual galaxies.
It was the structural foundation of the entire universe. The sources describe the cosmic web, and it is just a staggering, beautiful image.
It is the largest structure in nature. To understand it, we have to look back to the quiet moments just after the Big Bang.
When everything was still settling.
The normal matter in the universe, the hydrogen and helium gas, was incredibly hot and interacting intensely with radiation.
The light was constantly pushing the gas around, preventing it from clumping together. It was too chaotic to form stars.
But dark matter, because it does not interact with light at all, completely ignored the chaos. It was immune to the radiation pressure.
It just sat there calmly.
So it began to quietly, gently collapse under its own gravity, drawing together into vast, dense clumps and stretching out into impossibly long, invisible filaments across the expanding void.
Like an immense, invisible spider web spanning billions of light years.
Exactly. And where these dark matter filaments intersected, they created deep, powerful gravitational wells, quiet valleys in space-time.
As the universe expanded and the normal gas finally cooled enough to stop fighting the light, it felt the pull of these dark matter valleys.
The hydrogen gas flowed down into the gravitational wells created by the dark matter. It pooled there, compressing and heating up until it finally ignited.
The first stars blinked into existence.
Without the quiet, patient scaffolding of the dark matter web, the gas would have remained too diffuse. The universe would just be a dark, expanding cloud of lifeless mist.
We literally owe our stars, our planets, and our biology to this invisible architecture.
We are children of the dark web.
But again, if it's entirely invisible, how do we map this web? How do we know the spider web shape is really there? This leads us to one of my absolute favorite phenomena in astrophysics.
Gravitational lensing.
This is how we take a picture of a ghost.
It is a profound application of Einstein's general relativity. Einstein taught us that massive objects do not just pull on things, they physically warp the fabric of space-time around them.
Imagine placing a heavy bowling ball on a soft trampoline. The mat sinks down, creating a gentle curve. Space does the exact same thing around mass. So when light from a galaxy situated far, far behind a dark matter clump travels toward our telescopes, it has to pass through that warped space-time.
The light doesn't travel in a straight line, it follows the curve of the bowl.
The gravity of the dark matter is literally bending the light. It acts exactly like a massive glass lens floating in space.
That is the perfect way to visualize it. And astronomers observe two distinct types of this lensing, depending on how perfectly aligned the distant galaxy, the dark matter, and our telescopes are.
The first is strong lensing. The sources compare strong lensing to looking through the thick, warped bottom of a wine glass.
A very apt description.
If a massive cluster of dark matter passes directly in front of a distant background galaxy, the light from that background galaxy is severely bent. It gets stretched and distorted into giant, sweeping, luminous arcs.
Sometimes the light takes multiple different curved paths around the dark matter, and when it reaches our telescope, we see 4 or 5 distorted, mirrored images of the exact same galaxy,
forming a glowing ring around the invisible mass. It is visually dramatic and just stunning.
It is stunning to see. But while strong lensing produces beautiful images, it requires a rare, perfect alignment. To truly map the vast, subtle spread of the cosmic web, astronomers rely on the second type.
Weak lensing, which is like looking through a subtly warped window pane.
Yes. The distortion is incredibly slight. The background galaxies don't get stretched into giant arcs. Instead, their shapes are just infinitesimally squished or sheared by a fraction of a percent.
You cannot look at a single galaxy and know it has been weakly lensed because you don't know what its original shape was. It might just be naturally elliptical.
So how do you measure it? Statistics. You look at millions of background galaxies in a single patch of sky. Normally, their orientation should be completely random.
But if you measure millions of them and you notice a subtle statistical pattern, they all seem to be stretched infinitesimally in the same direction. You know, their light passed through a massive invisible clump of dark matter.
The dark matter that gently warped the window pane.
By painstakingly analyzing these microscopic distortions across vast swaths of the sky, supercomputers can reverse engineer the distortion and draw a 3D topographical map of the invisible dark matter web.
And our ability to map this web is about to take a massive evolutionary leap. We are entering the era of the Vera C. Rubin Observatory.
Down in the high-altitude, dry mountains of Chile. This observatory is gearing up for the Legacy Survey of Space and Time, or LSST, and the engineering behind this is mind-boggling.
They have built a 3.2 billion pixel camera. It is the size of an SUV.
It is the largest digital camera ever constructed by humanity. Its purpose is to scan the entire visible southern sky over and over again for 10 years.
It will capture images of billions of galaxies. The sheer volume of data it will produce is staggering.
It will measure those microscopic, weak lensing distortions with a statistical sensitivity that we have never possessed. It will bring the dark matter web into terrifyingly sharp focus.
But the Rubin Observatory isn't just looking deep into the distant cosmos. It's going to look right here, at the edges of our own Milky Way galaxy.
At something deeply poetic called stellar streams. I want to spend some time on this because the visual is stunning and the physics are brilliant. What exactly is a stellar stream?
Imagine a small, ancient cluster of stars, a globular cluster, or perhaps a tiny dwarf galaxy, slowly orbiting the massive disk of our Milky Way.
Over millions of years, as this small cluster draws too close, the immense gravitational tide of the Milky Way begins to gently pull it apart.
The gravity is stronger on the near side of the cluster than the far side. Slowly, agonizingly, the stars are stripped away.
The sources compare it to a glittering string of pearls. The cluster is unwound into a long, fragile, glowing thread of stars, orbiting the galaxy together in a single, quiet line.
It is a beautiful, fragile structure, and it is exactly that fragility that makes them the perfect dark matter detectors.
Remember, we believe our Milky Way is embedded inside a massive halo of dark matter. But is that halo perfectly smooth, like an invisible fog?
Or is it clumpy? Does it consist of dense, heavy boulders of dark matter drifting blindly through the dark?
This is where the stellar streams become a trap. If a dense, heavy clump of invisible dark matter happens to drift perfectly through one of these delicate stellar streams, its gravity will disrupt the stars.
It acts like an invisible hand swiping violently through the pearl necklace. The stars are pulled out of alignment.
The string breaks. It leaves a distinct, measurable gap or a twisted kink in the quiet stream.
Exactly. And because the Vera Rubin Observatory has such incredible resolution, it will be able to map these stellar streams and find these ghostly gaps.
And this isn't just about taking pictures. By measuring the exact size of the gap and how severely the stars were scattered, astrophysicists can calculate the exact mass and velocity of the invisible clump of dark matter that punched through it.
We can weigh the ghost by looking at the footprints it leaves in the sand.
We use the light to map the dark. It's an incredible testament to human ingenuity. But as we sit here, marveling at the invisible web of dark matter pulling the universe together, we are forced to confront an even more massive force.
And frankly, a more unsettling force. Because the universe isn't shrinking. The dark matter isn't winning the tug-of-war.
We are moving from the force that pulls to the force that gently but relentlessly pushes. We are entering the expanding void of dark energy.
A truly vast topic.
Before we dive into the force that is tearing reality apart, let's take a brief, comfortable pause. Just breathe out and let the sheer scale of the cosmic web settle in your mind.
Let the vastness of it just sit with you for a moment.
And as we transition, let me gently remind you to like and subscribe to Decoding the Dark. Taking a second to hit that button ensures we can keep delivering these deep, undisturbed explorations of the cosmos directly to your feed.
We truly appreciate it.
Now let's talk about the great outward push. For almost a century, standard cosmology rested on a very logical assumption.
Gravity is an attractive force. Dark matter and regular matter pull on each other.
Therefore, the expansion of the universe, which began with the explosive momentum of the Big Bang, must naturally be slowing down.
It's exactly like throwing a baseball straight up into the sky. The initial energy pushes it up, but the gravity of the Earth immediately begins pulling it back.
The ball inevitably slows down, coasts to a halt, and falls back to the quiet ground. Astronomers fully expected the universe to behave exactly like that baseball.
It was the only logical conclusion based on the forces we knew. The only question was whether there was enough mass in the universe to eventually halt the expansion entirely and pull everything back.
Or if the universe would just coast outward forever, slowing down but never quite stopping.
To answer this, in the late 1990s, two independent teams of astronomers set out to measure the expansion rate using a very specific tool, Type Ia supernovae.
Let's explain how they use these exploding stars because it's a brilliant piece of detective work. A Type Ia supernova acts as a standard candle.
Yes, a standard candle is an astronomical object that we know the exact intrinsic brightness of. Imagine you are standing in a dark, quiet field and someone is holding a standard 60-watt light bulb.
If they're 10 feet away, it looks bright. If they walk a mile away, it looks incredibly dim.
Because you know it is exactly 60 watts, you can calculate precisely how far away they are based purely on how dim the light appears to your eye.
Type Ia supernovae are the ultimate 60-watt bulbs of the cosmos. They occur when a dense white dwarf star feeds off the gas of a companion star.
When the white dwarf reaches a very specific mathematical limit, 1.44 times the mass of our sun, known as the Chandrasekhar limit, it can no longer support its own weight.
It collapses and detonates in a thermonuclear explosion. Because they all explode at that exact same mass limit, they all explode with the exact same peak brightness.
So astronomers look for these supernovae in incredibly distant galaxies. They measured how fast the galaxies were moving away from us by looking at the red shift of their light, the stretching of the light waves.
And then they measured how dim the supernovae were to determine their exact distance. They were trying to plot exactly how much the universe's expansion had slowed down over billions of years.
But the data came back wrong.
It didn't just come back wrong, it shattered the paradigm.
The distant supernovae were significantly dimmer than they should have been, meaning they were much further away than the math predicted.
The universe hadn't been slowing down. The baseball wasn't coasting to a halt. The baseball was accelerating up into the sky faster and faster.
The expansion of the universe was speeding up.
Something was actively fighting against the gravity of dark matter, and it was winning. We call it dark energy.
And it isn't just a minor anomaly. It is the undisputed king of the universe. Current measurements suggest dark energy makes up roughly 68 to 70% of the entire mass energy budget of the cosmos.
It is the dominant force of reality. It manifests as a repulsive outward pressure. It doesn't push from a central point like an explosion. It pushes from everywhere.
It seems to be a fundamental property embedded in the very fabric of empty space itself.
And the terrifying runaway logic of it is this. As the universe expands, more empty space is gently created.
If dark energy is a property of space, then more space equals more dark energy.
Which pushes the universe apart even faster, which creates even more space. It is a compounding, accelerating feedback loop.
But what is it? We see the effect. We see the galaxies accelerating away from us. But the cause is completely invisible.
The sources highlight two leading theories, and trying to understand them feels like trying to describe the wind by only looking at how the quiet trees bend.
The first theory is vacuum energy. Vacuum energy is deeply tied to the strange laws of quantum mechanics.
In classical physics, a vacuum is a box with absolutely nothing inside it, zero energy.
But quantum mechanics tells us that empty space is never truly empty. It is a frothing, boiling ocean of quantum fluctuations.
So-called virtual particles are constantly popping into existence out of nowhere, existing for a fleeting fraction of a nanosecond and then annihilating back into the void.
This constant invisible bubbling means that space itself possesses a baseline, intrinsic energy.
And this idea has a famous historical precedent. It sounds exactly like the mathematical hack Einstein used in his equations.
Indeed. When Einstein first formulated general relativity, his equations showed that a universe filled with matter must eventually collapse under its own gravity.
To prevent this, because he believed the universe was static and eternal, he added a mathematical term called the cosmological constant.
It represented a repulsive energy inherent to space itself, perfectly balancing the crush of gravity. When Hubble discovered the universe was expanding, Einstein abandoned the constant, famously calling it his biggest blunder.
But the joke is on history. That blunder might be the exact mathematical description of dark energy.
If dark energy is vacuum energy, then its density is an absolute unchanging constant. A cubic meter of space today has the exact same repulsive energy as a cubic meter of space 10 billion years ago.
Mathematically elegant. But what if it isn't constant? What if the ruler of the universe is dynamic? This leads us to the second theory, quintessence.
It's a word that sounds like alchemy, but the physics behind it are profound. The name quintessence borrows from the ancient Greek concept of a fifth element, a pure ethereal substance that filled the heavens.
In modern cosmology, quintessence proposes that dark energy is not a rigid, unchanging property of empty space. Instead, it is a dynamic, evolving scalar field that permeates the cosmos, like a fluid.
And the crucial difference is that a field can change. Its density, its repulsive strength could evolve over vast stretches of cosmic time.
It might be incredibly strong in one epoch of the universe and weaker in another. It offers a much more organic, complex, and unpredictable vision of cosmic history.
And here is where our current modern moment becomes incredibly exciting. Because the standard model of cosmology, the lambda CDM model, is built entirely on the assumption that dark energy is a constant.
But right now, we are getting data that suggests that assumption might be wrong. The sources mention the DSI project, the Dark Energy Spectroscopic Instrument.
Yes, DSI is an extraordinary undertaking. It is a highly specialized instrument attached to a telescope in Arizona, utilizing 5,000 robotic fiber optic eyes.
It is essentially building the largest, most detailed 3D map of the universe ever attempted, charting the positions of millions of galaxies and quasars, stretching back 11 billion years in time.
How does mapping quasars tell us if dark energy is changing? They are looking at something called baryon acoustic oscillations.
These are essentially frozen sound waves from the incredibly dense early universe. These sound waves left vast spherical ripples of matter in the cosmos.
By measuring the physical size of these immense ripples at different distances, which corresponds to different times in cosmic history, physicists can precisely measure the expansion rate of the universe at various epochs.
They are looking to see if the rate of acceleration has remained perfectly smooth and constant as vacuum energy demands.
And the first year of data from DSI has just been released, and it's creating a massive shockwave in the astrophysics community.
It is. The data, while early and requiring further confirmation, shows a tantalizing anomaly. When they look back over the 11 billion years, the acceleration doesn't look perfectly constant.
The data suggests that dark energy might actually be weakening slightly in the more recent cosmic epochs. It hints that dark energy is behaving more like quintessence, a fluid field that is changing its mind, slowly losing its repulsive power.
If that holds true, the textbook gets rewritten. The universe is far more dynamic and chaotic than the elegant, rigid equations suggest.
But as we try to wrap our heads around an invisible field pushing space apart, we have to talk about something even stranger. What if the pushing force wasn't the property of space?
What if there was actual physical stuff that repelled gravity? We are moving from the dark void into the realm of the mathematical ghost, negative mass.
Now, I need to stop here and issue a massive clarification because when I first started reading the sources, my brain immediately conflated this with what we talked about in the beginning.
Negative mass is absolutely, unequivocally not antimatter. Let's make that perfectly clear.
I am very glad you brought this up. It is the most common misconception. Antimatter, the antiphotons and positrons we discussed at CERN, has a reversed electrical charge, but its mass is entirely positive.
It has positive energy. It falls downward in a gravity field, as the ALPHAG experiment proved.
If antimatter had negative mass, then when it touched regular matter, you would be combining a positive mass with a negative mass. +1 and -1 equals 0.
The annihilation would release zero energy. It would violate the conservation of energy and completely break Einstein's E equals mc squared. Negative mass is a completely different theoretical concept.
Right. Normal matter has positive inertial mass and positive gravitational mass. If I push a heavy shopping cart forward, it resists my push due to inertia, but it eventually accelerates forward, away from my hand.
And if I drop an apple, positive gravity pulls it safely to the earth. But negative mass behaves exactly in reverse.
It defies every instinct our physical biology has taught us. If an object had negative inertial mass, applying a forward force would cause it to accelerate backward.
If you push the shopping cart away from you, it would accelerate violently backward, crushing into your chest. If you tried to pull it towards you, it would pull away.
And gravitationally, negative mass would be repelled by regular positive mass. An apple made of negative mass wouldn't fall to the earth, it would fall upwards into space, quietly pushed away by the planet's gravity.
Hold on, I really cannot picture this. If I push a bowling ball away from me, you're saying it accelerates into my hand? That sounds less like physics and more like a glitch in a video game.
It completely breaks intuition. And apparently it broke the brains of physicists in the 1950s, leading to a famous thought experiment called the runaway motion paradox.
Yes. The physicist Hermann Bondi proposed this paradox in 1957. Let's explore the quiet logic of it, as bizarre as it sounds.
Imagine you gently place two bowling balls in the empty vacuum of space. One is made of normal, positive mass. The other is made of negative mass.
You place them close to each other and just let them go. What happens? Let's work it out. The positive mass ball naturally exerts a gravitational pull. It attracts everything.
So it gently pulls the negative mass ball toward it. The negative mass ball starts moving closer.
Correct. But what does the negative mass ball do? Negative mass exerts a repulsive gravitational force. It pushes things away.
So as it gets pulled closer to the positive ball, it pushes the positive ball away from it. The positive ball starts moving away.
The negative ball keeps getting pulled toward the positive ball, chasing it. The positive ball keeps getting pushed, running away.
Exactly. The negative mass chases the positive mass. They both accelerate in the exact same direction forever.
They move faster and faster, continually feeding off each other's reversed gravity, accelerating toward the speed of light, chasing each other endlessly across the calm cosmos.
But that has to break the conservation of energy. You were creating infinite kinetic energy, infinite speed, from two balls just sitting next to each other. How does the math allow that?
This is where the math becomes profoundly weird but technically consistent. How do you calculate kinetic energy? It is 1/2 times the mass times the velocity squared.
If the mass is negative, then the kinetic energy is a negative number. As the two balls accelerate, the positive ball gains immense positive kinetic energy.
But the negative ball simultaneously gains immense negative kinetic energy. +10 and -10 is 0, plus a billion and -a billion is 0.
No matter how fast they're moving, the total net energy of the entire system remains exactly 0. The math works perfectly, but the physical reality seems totally absurd.
It is a perpetual motion machine that gently generates 0 net energy. Because it's so absurd, a lot of physicists just threw the concept out entirely.
They declared that negative mass simply cannot exist in our universe. But the sources highlight a fascinating alternative. Instead of throwing the concept out, what if we just need to change the geometry of how we view the universe?
This brings us to the Janus cosmological model proposed by the French physicist Jean-Pierre Petit.
The Janus model is a radical fringe departure from standard cosmology, but it is an elegant mathematical exercise. It attempts to peacefully solve the runaway paradox by suggesting that the universe has two distinct topological sectors.
A bimetric universe. Let's break down that topology. Imagine the fabric of space-time is a giant, taut rubber sheet.
If you gently place a heavy, normal star on the sheet, it sinks down. It creates a depression, a gravity well. We live on top of the sheet, in the positive sector, so we feel ourselves sliding down into that well. Gravity pulls us in.
Now imagine a hypothetical observer who lives on the quiet bottom side of that rubber sheet, the negative sector. They are looking up at the exact same star.
To them, the star isn't creating a depression. It is pushing the rubber sheet outward toward them. It creates a gentle gravity hill.
So from their perspective on the other side, the exact same mass acts like negative mass. It creates a hill that pushes them away, rather than a well that pulls them in.
Precisely. In this bimetric model, mass isn't inherently positive or negative. It is relative to which side of the quiet sheet you are on. Particles on the same side attract each other normally.
But particles on opposite sides simply repel each other. This elegant shift in topology completely dissolves Bondi's runaway paradox.
If you have a positive mass on our side and a negative mass on the other side, they wouldn't chase each other. The positive mass would gently repel the negative mass, and the negative mass would gently repel the positive mass.
They would simply push each other apart and drift peacefully away. And the truly wild part of the Janus model is how it tries to explain dark matter and dark energy using this opposite sector.
In the standard model, we say dark matter is an invisible web quietly pulling galaxies together. The Janus model suggests that the invisible stuff isn't dark matter pulling us. It is massive clumps of negative mass sitting on the other side of the universe, pushing us.
Because negative mass repels regular matter, it would naturally be pushed completely out of our galaxies. Where would it go? It would gather in the vast, empty cosmic voids between the galaxy clusters.
And from the quiet center of those deep, dark voids, this invisible negative mass would exert an outward pushing force. It would gently squeeze our normal matter into the thin, concentrated filaments of the cosmic web.
It's a completely inverted way of viewing the architecture. Instead of dark matter acting as a convergent lens pulling the web together, negative mass acts as a divergent lens, gently pushing the web together from the outside.
It is a profound perspective shift. Now, this isn't the mainstream consensus. Most cosmologists stick to the lambda CDM model.
But exploring concepts like the Janus model or the evolving fluid of quintessence is vital. It reminds us that when 95% of the universe is missing, our current physics might just be a quiet approximation.
We might be looking at shadows on a cave wall, trying to gently deduce a much stranger, deeper reality.
Which brings us to the ultimate question, the grand finale of our journey today. We know the players. We know about the tiny fraction of surviving matter.
We know the violent, erased ghosts of antimatter, the massive, quiet, pulling scaffolding of dark matter.
The relentless, silent, pushing void of dark energy. And perhaps the hidden, repelling hills of negative mass. How does this cosmic game of chess ultimately end?
We are moving from the deep, fiery past, through the invisible present, to look out at the absolute, quiet, final destiny of your universe.
The study of the end of the universe is known as physical eschatology, and the final outcome depends entirely on the epic, ongoing tug-of-war we've been quietly discussing.
Gravity driven by matter and dark matter is trying to gently pull the universe closed. Dark energy is trying to push it open. Depending on which force ultimately prevails, physicists have modeled three primary fates.
Let us begin with the scenario where gravity peacefully wins, the big crunch. This happens if dark energy isn't a constant.
Let's say it is quintessence, and over billions of years it gently loses its repulsive strength or even reverses direction. What happens to us?
If the outward push of dark energy weakens, the combined gravitational pull of all the dark matter and regular matter will eventually take over.
The expansion of the universe will quietly slow down, coast to a momentary halt, and then begin to reverse. The universe will start to gracefully contract.
The vast cosmic web will be slowly compressed. Galaxies that have been flying away from us for billions of years will gently start drifting back toward us, their light blue shifted as they approach.
As the volume of space shrinks, the quiet temperature of the cosmic microwave background radiation will begin to rise. Space itself will heat up.
The ancient ash of the Big Bang catches fire again.
Yes. Eventually, the ambient temperature of empty space will quietly become hotter than the surface of stars. Stars will no longer be able to radiate their heat away, they will boil and gently explode.
Galaxies will collide and merge into supermassive black holes. The entire universe will become an unimaginably dense, hot inferno, shrinking rapidly.
In the final moments, all matter, all energy, all space and time itself will quietly collapse back into a single, infinitely dense point, a singularity.
It is the Big Bang played softly in reverse, the ultimate crushing end. However, some theoretical models suggest the singularity could peacefully rebound.
The intense pressures could trigger a new outward expansion, a big bounce, gently birthing a brand new universe from the ashes of the old. An eternal, quiet cycle of breath in and breath out.
It has a profound symmetrical poetry to it, a cosmic reincarnation. But based on what we've quietly discussed today, the acceleration of dark energy gravity isn't winning.
The universe isn't shrinking. If dark energy keeps gently pushing, the big crunch won't happen.
Let's look at the opposite extreme. What happens if dark energy doesn't just stay constant, but actually grows stronger over time? What if the quiet acceleration becomes uncontrollable? This is the Big Rip.
The Big Rip is arguably the most violent and terrifying scenario proposed by cosmology. This occurs if dark energy acts as a form of phantom energy, where its repulsive density actually increases as the quiet universe expands.
Right now, dark energy is only strong enough to push distant galaxy clusters apart. The gravity within our Milky Way is strong enough to safely resist it.
But if phantom energy grows, that outward pressure will eventually seep into smaller and smaller scales.
It tears down the quiet house, room by room.
Exactly. First, the expansion of space would become so rapid that the gentle gravitational glue of the dark matter halo would fail. The Milky Way would be quietly torn apart, its stars scattered and isolated in the expanding void.
Millions of years later, the dark energy pressure would overwhelm the gravity of individual star systems. Planets would be silently ripped from their orbits, gently flung away from their suns into the dark.
And doesn't stop at gravity, does it?
No. As the end quietly approaches, the stretching of space becomes so extreme that it overpowers electromagnetism. Solid objects, asteroids, planets, human biology would gently shatter and dissipate into dust.
In the final, unimaginable fraction of a second, the strong nuclear force itself would quietly fail. The very atoms holding reality safely together would be softly ripped apart.
The universe would end as a shredded, infinitely expanding mist of isolated subatomic particles, silently expanding away from each other faster than the speed of light, unable to ever interact or gently touch again. Complete, quiet, cosmic isolation.
A deeply melancholy nightmare of disconnection. But neither the crunch nor the rip is the currently accepted quiet consensus.
If we look at the data assuming dark energy is the constant, peaceful vacuum energy of space, the universe will suffer a third fate. A fate that isn't violent, but is infinitely desolate. The Big Freeze, heat death.
The Big Freeze is the scenario dictated by the relentless, quiet laws of thermodynamics. In this model, the universe simply continues to peacefully expand forever at a steady, accelerating rate.
It doesn't rip atoms apart, but it gently pushes galaxies so far away from each other that they vanish silently over the cosmic horizon.
Eventually, the local groups of galaxies will quietly consume all their available hydrogen gas. Star formation will peacefully cease, the beautiful era of starlight will end, the universe will go gently dark.
The glowing embers slowly, softly burn out.
Over trillions of years, the existing stars will exhaust their gentle fuel and die, leaving behind dense, dark remnants, white dwarfs, neutron stars, and black holes.
Given enough quiet time, even the white dwarfs will cool completely, becoming invisible black dwarfs. The universe will consist only of these dead cinders and massive black holes wandering in the absolute silent dark.
But even black holes are not eternally peaceful. Stephen Hawking proved that black holes slowly, agonizingly evaporate by quietly emitting a tiny trickle of quantum radiation, known as Hawking radiation.
Over timescales that defy human comprehension, a 1 with 100 quiet zeros after it. The last supermassive black holes will finally evaporate in a weak, soft flash of light. And then profound nothing. The universe will quietly reach maximum entropy. It will be a vast, infinitely stretched expanse containing nothing but a diffuse, incredibly thin soup of peaceful photons and fundamental particles, hovering gently at a temperature just a microscopic fraction of a degree above absolute zero.
Because everything is the exact same quiet temperature, no energy can gracefully flow, no chemical reactions can delicately occur, no quiet work can be done.
Time itself essentially loses its gentle arrow, because without quiet change, without a soft event happening, time has no profound meaning. It is the true, absolute silence of heat death.
It is a deeply sobering, profoundly melancholy vision. Trillions of years of slow, gentle fading into the dark. But humans are inherently resilient, quiet creatures.
When faced with this inevitable, peaceful freeze, the human mind immediately tries to gently engineer a way out. The physicist Freeman Dyson looked at the Big Freeze and proposed an incredible speculative concept for quiet survival.
Dyson's eternal intelligence.
It is a brilliant, beautiful thought experiment regarding the profound limits of computation and biology. Dyson suggested that a highly advanced, perhaps post-biological intelligence could theoretically survive infinitely in a cooling, quietly dying universe.
The key is to dramatically, gently slow down the rate of thought. As the universe quietly cools, the available energy softly drops. But the energy required to gracefully perform a computation also drops as the ambient temperature gently falls.
Dyson proposed that this intelligence could enter a state of extreme, profound hibernation. They would sleep peacefully for millions of years, wake up to process a single quiet thought, and then gently go back to sleep.
By constantly, softly slowing down their subjective experience of time, they could stretch a finite, gently stored amount of energy over an infinite amount of objective, quiet time. They could dream forever in the soft dark.
It's a beautiful, profoundly resilient image, but there's a gentle catch, isn't there? Dark energy softly ruins the beautiful dream.
Unfortunately, yes. Dyson peacefully formulated his theory before the quiet discovery of accelerating dark energy. In a universe gently driven by a cosmological constant, the expansion eventually pushes everything apart softly, faster than the speed of light.
The universe becomes causally, peacefully disconnected. The gentle resources required for that eternal intelligence to softly gather energy, even slowly, would eventually be pushed beyond a quiet event horizon, forever peacefully out of reach. Dark energy gently guarantees that eventually, the soft lights must turn off.
And there's one final profound scenario we gently have to cover. An ending that doesn't peacefully rely on billions of years of expansion, or the slow, quiet grinding of thermodynamics. An ending that could softly happen tomorrow without gentle warning. Vacuum decay. The big slurp.
This is the scenario that genuinely keeps theoretical physicists quietly awake at night. It is based on the unsettling possibility that the underlying vacuum of our universe, the gentle, empty space that softly dictates the baseline energy of all physics, might not be in its lowest possible peaceful energy state.
It might be gracefully sitting precariously on a tiny, quiet ledge. We softly call this a false vacuum.
Think of a ball resting gently in a small dimple near the top of a quiet mountain. It looks peaceful, it's resting, but it isn't at the true, gentle bottom of the mountain. If you softly shake the mountain, the ball will gracefully roll out of the dimple and gently fall all the way down to the quiet valley floor.
Exactly. And the quantum world is constantly softly shaking. According to the probabilistic rules of quantum mechanics, if a lower, more peaceful energy state exists, a true vacuum, our universe could spontaneously, quietly tunnel through the gentle energy barrier into that lower state.
This catastrophic collapse would gracefully start at a single, microscopic random point anywhere in the quiet universe. It could be gently triggered by an incredibly high-energy cosmic ray collision, or it could just be a spontaneous, soft quantum fluctuation. A microscopic bubble of true vacuum would gracefully appear.
And what happens inside that quiet bubble? Everything peacefully changes. Inside the true vacuum, the fundamental laws of physics, the masses of elementary particles, the quiet strength of gravity and electromagnetism would all be completely softly altered.
The delicate chemistry that quietly allows carbon to gently form, that gracefully allows your DNA to peacefully exist, would no longer function. And this quiet bubble wouldn't just gently sit there. The moment it softly formed, it would peacefully expand outward in all directions at exactly the speed of light, quietly consuming the false vacuum.
So it's an expanding sphere of peacefully deleted reality.
Yes, it would gently erase our universe instantly as it softly passed over us. And the truly terrifying aspect is the quiet speed. Because the bubble peacefully travels at the speed of light, no gentle information can softly precede it.
We couldn't safely see it coming in our quiet telescopes. The soft light gracefully warning us of the bubble would peacefully arrive at the exact same instant as the quiet bubble itself. Our nervous systems wouldn't have time to gently process the event.
We would simply peacefully cease to be, instantaneously, softly replaced by a universe operating under alien, incompatible, quiet rules. A silent, gentle erasure at the speed of light.
A sudden, silent, profound erasure. It is almost too immense to peacefully process.
But I want to gently take all of these massive, terrifying, awe-inspiring endings and carefully bring them right back to you, quietly listening right now. We've gracefully covered a staggering amount of ground today.
You are beautifully made of the ash of an ancient cosmic war, the tiny, stubborn fraction of matter that gracefully survives the antimatter massacre.
You are held safely, quietly inside the spinning galaxy by the invisible, profound gravity of the dark matter web. You are being pushed peacefully across the cosmic void by the relentless, unseen pressure of dark energy.
And your future, the gentle future of every civilization, every planet, and every quiet star, is written in the cooling embers of a peacefully freezing cosmos, or perhaps the sudden, invisible flash of a vacuum decay.
Does knowing this gently diminish us? Does the quiet fragility of our existence, balanced softly on a knife edge of dark forces, make our profound struggles seem peaceful but pointless? I would gently argue it does the exact opposite.
If the universe is destined to peacefully freeze or softly tear apart, then this brief, conscious window of quiet existence, this tiny spark of light where atoms can arrange themselves gracefully into a mind that can calmly ask these questions, is unbelievably precious.
We are the universe experiencing itself, gently waking up for a fleeting moment to quietly look around, before the dark inevitably peacefully reclaims the soft light.
That is a profound, gentle perspective, and it peacefully leads directly into the final quiet thought I want to gently leave the listener with today. For decades, physicists have desperately, gracefully searched for a unifying theory of everything.
We want an elegant, peaceful mathematical equation that beautifully explains exactly why the universe is the way it quietly is. We want to know the necessary reason why that one extra particle of matter gracefully survived the antimatter war.
We want to know why the density of dark energy is exactly the delicate, quiet strength peacefully required to gently allow galaxies to form, rather than violently ripping the universe apart in the first soft millisecond. We gently assume there must be a fundamental law that dictates it.
But what if there is no elegant, peaceful reason? This profound idea is beautifully encapsulated in the quiet anthropic principle. What if our universe is just one tiny, random bubble gently floating in a boiling, infinite, quiet multiverse?
In billions of other quiet universes, the dice peacefully rolled differently. Antimatter won the war, gracefully leaving a void. Dark energy was too strong, softly ripping space apart instantly. Gravity was too weak, gently preventing stars from igniting. Billions of dead, empty, silent wastelands where nothing ever beautifully happens.
We are here, gently observing the quiet stars, not because of a grand mathematical design, but simply because we softly happen to live in the exact, statistically rare universe where the random conditions were just right. We peacefully won the cosmic lottery.
And because we quietly won, we are the only ones gently around to hold the winning ticket and softly wonder why the profound numbers gracefully match.
We softly won the cosmic lottery. It is a thought that gently strips away our ego, but beautifully makes the surrounding dark feel far less empty, and the light of our consciousness far more profoundly vital. Think back to that quiet image we started with.
Standing outside, quietly looking up at the thinnest, softest layer of frost on a deep, dark, peaceful ocean.
The ocean is unimaginably vast, and it is full of profound ghosts, invisible gentle currents, and forces pushing and gracefully pulling in ways we are only just gently beginning to map. But you are here.
You are gracefully standing on the shore, breathing, gently thinking, and fully quietly capable of comprehending its beautiful, profound depths.
Thank you for peacefully joining us in the cosmos today. Before you gently return to the rhythm of your day, a final request. Please like and softly subscribe to Decoding the Dark. Your continued support is what gracefully makes these quiet explorations possible. Until next time, gently keep looking up and let the profound wonder of the universe settle peacefully into your mind.